capital pi, what did we call that? The selection operation, oh, I don't remember. I know that it filters out, and I shouldn't really use the word selects again, but what it does is it only returns values from the columns that are defined within that predicate. And so usually it's a set of column names in that predicate. It's different from the predicate of the selection operation, which usually has some sort of conditional that evaluates it evaluates its rows by, and it can have a multiple column values in there. I just have a simple one on the board, salary less than 50K. Projection, that's what capital pi is. That's the projection operation. And projection really just defines which columns will be shown out of whatever is retrieved. And usually we're going to have if we have projection in our equation that we're writing with these operations, we're going to do the selection first, get entire rows, and then projection will only keep certain columns from the rows that were returned. So usually the projection is wrapping the selection operation. And then we've got a couple lesser used fundamental operations. There's union, which basically concatenates table B onto the bottom of table A, as long as both A and B have exactly the same design, right? The same number of columns and the same data types. And then we have the differencing operation, that minus sign there, and that is, I believe, the definition that I gave you on Monday was that it is going to return all rows from A that are not in B. That makes sense in terms of a differencing operation, or maybe it's called the subtraction operation. I have examples on the whiteboard of those things. I already talked about retrieving all the instructor records from whose salaries are less than $50,000 on campus, and so we'll get all of the English professors in there. And if we want to generate a list of everybody, of all faculty, all instructors on campus, and their salaries, we just want to see the columns name and salaries, then that's where we're going to use a projection operation. So that's my second example there, project all of the names and salaries from instructor. And we're assuming, since there's no selection operator inside those parentheses, it's basically select all from instructor. There is no predicate that we need to grab. So if we just have a table name, you can imagine that's just select table name without a predicate. And so as an example of when we would use union, again, we need to have two tables that are union compatible. That is, they have the same number of columns and types of columns. And so I'm trying to grab all of my examples from your database schema. And so I'm going to grab the student table out of your schema, but I'm only going to grab the name column out of there. That's going to be a string data type. And I'm only going to grab the name data type out of the instructor table, and I'm just going to glue all of the instructor names onto the bottom of all the student names. And now, what is that? That's basically the entire, that's most of the population of campus right there. I guess we're leaving out administration and the cleaners and stuff like that. But all of the people that we normally see in classrooms in one list. If that's the type of list we were trying to generate, then union can generate us a list like that. How would I use the subtraction operation? What if I subtracted from the list of all student names all of the names of instructors? So print everything in the student list that does not have an instructor name in that. What do you suppose the user asked us to do that led us to put that statement together? Either we're listing all students on campus who don't have the same last name as an instructor, maybe that's what that's doing. So instructors, generally their kids can come to university for free, and we just want a list of all the kids who are actually paying for their education. Maybe that's what this list is. This is a list of people that we need to send bills to. Or I don't know, sometimes instructors are students. I don't know if you've ever been in a class where another instructor from somewhere on campus was sitting in the back of the class all semester long, because another benefit of being professors is we can take classes for free. We usually can't take a whole semester's worth of class, but one class per semester, we might, instead of doing office hours, go to a particular classroom and learn, learn some statistics class that we didn't have time for when we were your age. And so maybe we just want a list of all of the real students in class. We want to exclude all the professors that might be taking classes at that time. Again, to know who to bill. Okay, so those are examples of things that we've seen, and I don't know, hopefully, potentially, real world examples of when stuff like that might be used. Cartesian product is something that we would never actually choose to use. It's just something that gets used for us on the way to doing something that we would choose to use. So we're going to represent that with the operator capital X. I don't know if that comes from the Greek or not, but that's going to be the Cartesian product operation. So if I were writing names for these things, Cartesian product. And then, so I don't forget projection again. Projection and selection and union. I can write out that entire thing. And subtraction? I forget what that guy's name was. Differencing? All right. So Cartesian product takes two tables, just like union and subtract, but they don't need to be union compatible, like union and subtraction do, because this is also a concatenation, but it's not vertical concatenation. This is going to be horizontal concatenation. We are taking two separate tables and then just gluing them together horizontally. And so the way that that's described in your book is we are creating a whole new table, a whole new relation out of relations R and S, and that new relation is a concatenation of every tuple, every row in R, combined with every row in S. We are basically, for every row in the first table, taking every row in the second table and combining those two. And so if we've got 5 rows in the first table and 4 rows in the next table, the first 5 rows in the resulting table will all start with the first row in table R, and then have each different row from table S glued onto that. We'd end up with 20 rows, right? 20 combination rows in this new table. Does that make sense? Do you have an okay picture for that in your mind? That's the definition. And now I'm just going to show you examples with my Greek letter tables, blue tables that you saw on Monday. Let's say that my relations R and S are these two here. R has 2 rows in it. S has 4 rows in it. My prediction is the Cartesian product of these two tables will have 8 rows in it, and that table will have 5 columns in it, since we're going to concatenate all of the columns together, essentially, right? Every row is going to have 5 values on it. And would it surprise you if the first row, read from left to right, were alpha 1, alpha 10a, and the second row were alpha 1, beta 10a, and the third row were alpha 1, beta 20b. You see how these tables, these rows are going to go together in this new table that is represented by that Cartesian product operator, that X. This X is creating a whole new table. We're not giving it a new name. I'm not getting my laser pointer to fire here. I don't know. Oh, because I've got it turned off. That's why. So that operation is actually creating a whole new table that didn't exist before, and that table only exists in memory, and usually we're going to see that table inside parentheses inside our statement. So sometimes while executing a statement, a whole new table gets built, and then some other operator is called on that to project out columns or to select out rows according to some predicate. So this is some new table, and it's going to look like this. Does that table design make sense? And those table values, those row values? I think I already quoted to you the first 3 rows in there. So alpha 1 is being combined with all 4 rows in table S, then beta 2 from table R is being combined with all 4 rows in table S. So this is a workable example because it was only a table with 2 rows and a table of 4 rows, and so that gives us a maximum table of 8 rows out the other end. But you would not want me to put on a quiz something that has a table with 100 rows with another table with 50 rows, right? That would end up being 50 times 100, 5,000 rows in the resulting table. And so this is why the Cartesian product operation its reputation is it's extremely inefficient. It's actually number of rows times number of rows. That feels like n squared type of effort in order to do something like this. And from what you recall from CS2, probably you always hated timing those n squared time operations. Those took the worst amount of time to wait for. Even if it was only for 3 seconds that you had to wait for your answer, that was a long 3 seconds. Nobody likes waiting n squared time. Nobody likes to wait for n squared operations to terminate. And that's what Cartesian product feels like. And so you become a database nerd, you go off and talk with the other database nerds that you work with at the company, and you'll all be making jokes about the n squaredness of Cartesian product. Nobody respects Cartesian product for its efficiency. Here is an example from the real estate company, and of course we don't see the source tables again, because that book never lists them, but we do see how this thing was put together. First, we used a projection operation we grabbed out of the client table. It probably had more than 3 columns in it, but we're only grabbing out the client ID, the client number column, the first name column, and the last name column. And then from the viewing table, the table listing all of the customers that viewed a property that we saved into the database, we're grabbing out of that one the ID of those clients, the ID of the property they viewed, and then whatever comment they left. And what this capital X Cartesian product operator is doing is saying all of these rows will be combined with all of these rows horizontally. And so that means we're going to see a resulting table with client number, then first name, then last name, then client number again, then property number, then comment. And since these are 2 potentially different values, they get prepended with the table name that they came from. So we know which table those values came from. And then we can sort of see a pattern here. I see CR76, John, and K happen like 5 times with 5 different values in these rows. And then CR56, Aline Stewart, 5 times with 5 different values, with 5 different values in this table. And then CR74, Mike Ritchie, repeats 5 times with 5 different values in the right side. And CR62, Mary Trieger, appears 5 times with 5 different values in this table. You know what? I bet I can predict what the 2 source tables were for this result here. I bet the first table only had 4 rows in it: CR76, CR56, CR74, and CR62. And then this table had 5 rows in it. And it was CR56, CR76, CR56, CR62, CR56 It's these 5 values that are being combined with each of these 4 values from the first table. And that's what Cartesian product does. You as a programmer might implement it differently. You might combine all rows in the client table with every individual row in the viewing table, do it backwards, but you would still end up with the same result. They would just be probably in different orders. These guys would all be different, and these guys would repeat each other 4 times rather than 5 times. But either way, we're going to end up with number of rows in the R table times number of rows in the S table, rows in the resulting table. Right? M times N. Number of rows in R times number of rows in S. Make sense? I am not going to give you a real-world example of combining every row in one table with every row in another table, because there are no examples that really make sense in the real world. I guess we could come up with one, but again, the reason that this is a fundamental operation is because other operations that we would actually want to use in the database use that as a building block in order for them to be able to work. So, we don't have an SQL keyword for Cartesian product, but we do have keywords for commands that use the Cartesian product in order to do their jobs. And one of them is join. And you should have seen the join command in one of your first 2 homeworks in this class, right? When I forced you to take 2 or 3 tables and glue them together and then look at the resulting SQL code that you had operate when you drag and dropped fields from multiple tables together. You probably saw the keyword inner join, right? So that's the standard keyword that we see in SQL language. Actually, there's another keyword in the SQL language called natural join, but I tend to just focus on inner join. Natural join tries to make your life simpler for you, but it turns out that you almost never want to go with what the computer chooses for you in natural join, unless you designed your database very specifically so that natural join would always work, and that's a lot of effort a lot of times. You're after a few years of having a database in your company, you're not even the only one who's been creating tables in that database, and it's really hard to force everybody to program exactly the way you do, force everyone to design tables exactly the way you do. And so even if at the beginning of your career at the company, natural join worked pretty well with the tables you designed, by the end of your career at that company, when all the new kids being hired to help you with the database have been adding their crazy ass designs to the thing, suddenly only inner join works. But I'm going to talk about natural join anyway, because I've got a slide for it, and the book author talks about it. But what does it do? They say it's kind of like performing a selection, except that join keyword is actually selecting from multiple tables at once. And it's basically selecting the Cartesian product of 2 relations. And so basically, a join connects 2 tables together and combines every row with every row, and then pulls out a selection, a select predicate version. It's not going to grab all of the rows out of that Cartesian product. It's only going to grab certain rows out of that Cartesian product. And a lot of you probably already know which rows are going to be grabbed out of that Cartesian product just because of how you drag and drop things in that first homework or that second homework that involved the join. So, Because join operations require the Cartesian product in order to work. And since Cartesian product is one of the least efficient operations in the fundamental set of operations in a database, that means that your join operations are also going to be the most expensive time-wise, the least efficient operations to run in your database. And unfortunately, since the whole idea behind using a relational database is creating a separate table for every entity that you are dealing with in your database system, like for the university, we're dealing with student entities and instructor entities and room entities and course entities and advisor entities and time slot entities. It makes it easy to organize objects into their appropriate tables in that system, but it also forces you, when you're actually trying to ask a question where you need to combine multiple entities together, multiple tables together, it's going to force you to use the inefficient operation. And so the job is to implement the inefficient operation as efficiently as possible. And that is the real reason why there is a subroutine inside your database, that when you give it a command and say, okay, combine these three tables together and give me this result, this projection, this selection of columns out of that table that all match this predicate for this selection operator, then it's going to try 2 or 3 different ways of putting that monster table together, because some of those ways are going to end up being cheaper than others of those ways. So it's pre-processed and pre-analyzed before run on actual data. And the pre-processing is done with the data in the metadata database, data set of the database. That is the design of the tables, the schemas. We know what the data types are in each column and how wide, how much memory they cost. And so if we're going to put all that stuff together, then we know how wide the table in the final table in that join is going to be, and then those are the numbers that are used to figure out, okay, well, if the intermediary tables are this big, it's going to take this much time to generate them. But if we can get the same answer by generating a smaller intermediary table along the way, then that will be more efficient. That's the general idea of what's going on before the database even bothers to start retrieving your data. Is it figures out, I can do it this way, or this way, and which of these 3 ways is more likely to be more efficient. So let's start with natural join. We're joining 2 relations, my blue tables with Greek letter values. I've got a table R, I've got a table S. They're relations, that is, they are tables. And then their schemas, that is, the names of their columns, are the sets of names represented by capital R and capital S. And so capital R's schema is columns A, B, C, and D. And capital S's schema, the columns inside capital S, are columns B, D, and E. And here we are assuming that you would not have named 2 columns in 2 different tables B unless they held the same data. Right? We're going to assume that if you have a name column in the student table and a name column in the instructor table, we're going to assume that those are both name fields, and also those are both string fields, I should say. And also, those strings are the same size. Everything about them is going to be similar if you're using the same name. The meaning is going to be the same. This is the name that we give to this 2-legged, this bipedal person on campus. So that's what natural means in natural join. That's the assumption that comes with it. Is if you've got 2 separate tables with a same name column, that same name column has the same type of data in it. One's not going to be a string and the other is going to be an integer. No. In a natural database design, two columns with the same name will have exactly the same type of data inside them. We can count on that. That is what natural join counts on. So the natural join of tables R and S is going to be a new relation, a new table, and its schema is going to be the union of R and S. That is, if I'm looking at this, it's going to have columns A and B and C and D and E. Mathematically, we're not going to have two columns with the same name. So it's not going to be A, B, C, D, B, D, E. That's not what the mathematicians want to happen. Because there's also something else that's happening. So let me put uniqueness aside for now. In order for this to happen, it's going to be obtained as follows. Okay, they're giving us some sort of little algorithm here, some sort of pseudocode. We're going to look at every pair of tuples, T of R and T of S, because this tuple is being joined with this tuple, and then there's another row that is this tuple plus this tuple, and there's another row that's this tuple plus that tuple. So we're going to look at every pair of those tuples, one from table R and one from table S, and we're only going to put them in the final resulting table if T and R and T and S have the same values for each of the attributes in the intersection of R and S. And so before I said that these tables both had a column B with the same data in them, and I had been neglected to notice that they also have a column D. And again, it is the same data type, it's letters. And so this matches the assumptions that natural join makes. And so we're going to get a resulting table with unique names, but only the rows, combined rows from these two tables, keep on going the wrong direction. Only the combined rows from these two tables will go into this table that have the same values in columns B and D. So 1A and 1A, those two rows will be combined and that will be added there. In fact, I think I've done a little visualization. Again, okay, the author is T has the same value as TR from table R, and T has the same value as TS in table S for the intersection of the common column names between them. Okay, here comes there it is. Oh, did you see that? A red line just appeared from nowhere, Sam. Yeah. Nowhere. The technology. But you do see that for B and D, the values are the same for those two rows. And so that row is going, magic. That combined row is going to be added to that table. And so, I mean, since they have the same values, it doesn't really matter that we know which table they came from. And that's why we don't really need duplicate rows in the theoretical case. Now, in the real world, when you're using Microsoft Access, it is going to return the duplicate columns because that's what humans want. They're sort of nervous if the computer starts only showing, removing columns. And so it will always duplicate columns and then prepend the names for the columns that were the same from both tables. But in the theoretical, mathematical set theory case, mathematicians would prefer if only unique column names made it into the final table. So I don't think that's the only row that 1 alpha A will match with. I bet it's also going to match with this row, right? Because also 1A. So I should, there's my red line. And now that the red line has combined those two rows, that combined row will go into the result table, right? And I think now there's no row in table S that has the same values in columns B and D with that first column. And so now we're going to do the same thing with the first row. And so now we're going to do the same thing with the second row. So I'm looking for 2 A's. And I don't see any 2 A's as the first 2 values in table S, right? You know why I'm looking for 2 A's? It makes sense. So no rows will be put in the final table that are composed with beta 2, I forget what that symbol is. Gamma, beta 2 gamma A, because it doesn't, it can't, even though in the Cartesian product it combined with every single row, only those combinations that have the same values actually get transported into the final table. But, and same thing for the gamma 4 beta B row, there are no 4 B's in table S, and so no common value combinations can come out of that. But there are 1A columns, so alpha 1 gamma A will combine with 1A alpha, but only 1A actually makes it into the final table because duplicates are removed, duplicate columns are removed. And of course, since there's a second 1A there, then that row will combine with that column as well. And those are the only 2. Are there any 2B rows in table S? And so now that delta 2 beta B row will combine with this row, right? The 2 beta delta row. Oh, I guess I didn't print out that 4th row. But okay, there it is. Boom. And that's it. Those are the only combined rows that have matching values for the common column names. And that's what natural join does. And if you were the programmer who had to implement that, the code you would have to write would be first, match every row from column R with every row from column S, and in that resulting table, go down and for these common column names, check to see if the values are the same, and then if they are, then only take those rows and put them in the final table that you're going to return to the user, right? So you are using that Cartesian product table that was generated in the background. You never show it to the user, but you are doing all the work of processing that, building it, doing comparisons all the way down it, and then generating the new table that the user actually wanted. When you got an inner join in your assignment, this is exactly what was happening in the background. You never saw the Cartesian product while it was running. It only showed you your resulting table that matched, in my case, your movie actor names with your movie names, right? Your animal names with their categories. Your sports names with their sports team names with their colors. You only saw the stuff you cared about, the stuff that actually matched between the tables. Make sense? This is the biggest thing in relational databases. This is how your relational databases are made to work. If you're going to design your databases as a set of entities in tables, they have to go through this process in order to be joined together in a way that makes real-world sense to the users of the database. The downside is it's an expensive process. It's an n-squared-ish time process, but at least it's not exponential time. At least it's not n cubed. And at least there are different ways of combining the tables, so it's not the worst version of n squared for the table designs that you have. You're going to find a best of the bad cases to execute your query by. So that's natural join. And what did I say about natural join? Natural join assumes that same columns mean same data. Same values and meaning. And of course that means data types. Same data types. But really it's assuming that you know, if this is age of the students in the table, then this also means age of students in the table. Or I guess that this would be which year they are in at college. I guess that makes more sense. You're a freshman, sophomore, junior, or senior. And maybe there's a 5 in there for the 5-year seniors, and maybe there's a 10 in there for the graduate students or something. But we are really talking about meaning, and that meaning is encoded in the data type that's chosen for the values, interpreting the values that are in those columns. But when you looked at your SQL command for homework 2, it didn't say natural join. It said inner join. Probably before talking about inner join, we're going to see an example from the real estate company. No, okay, I guess this is just showing the source tables and result tables of natural join. But also, it's showing you the mathematical symbol, the symbol that we'll use to represent the mathematical operation. It's essentially that Cartesian product symbol, except we draw 2 vertical lines on either end. I call this the bow tie operator. That's natural join. And so for this, I would actually be able to come up with a real-world example if I thought about it. But I would rather move on. But I mean, the real-world examples are everything that you guys implemented in homework 2. Tie these 3 tables together on the basis of matching values to show sports teams and their colors. Or whatever it was that you implemented. Authors and the books that they wrote. So yeah, we're going to use the bow tie operator if we want to make the assumption that B means B means B means B. Everywhere you see it, it always means the same thing. And so if we're doing a natural join within our real estate world, we're going to grab out from the client table client IDs and first names and last names, and we're going to combine all of those rows with all of the client IDs and property numbers and comments from the viewing table, but we are only going to show the rows where in those combinations the common field names are the same, and there's only one common field name here. The intersection of these 2 schemas is client number, and so basically the client number in the client table has to be the same as the client number in the viewing table. That's exactly the type of application you guys did for homework 2, right? And so these results are actually results that make sense as compared to the Cartesian product results that I showed you before, a great big long table of 20 rows. But this is client number John K, who actually looked at property number PG4 and thought that it was too far out of town. And that's the only property that John K looked at. But apparently, Aline Stewart looked at 3 different properties. She thought this one was too small, and then she had no comments that she put down for those 2. Maybe she was too polite. Maybe she's considering one of them. And apparently Mary Trieger saw property number PA14 and didn't like the fact that it didn't have a big dining room, or any dining room at all, just a kitchen and a living room. Mary likes to give dinner parties. That would be a terrible house for dinner parties. All right? So natural join, it seems to me, seems to be the answer to all of my prayers. This is finally the operation that starts putting stuff together. It's not, natural join is not one of the fundamental operations. It's a combination of Cartesian product and other things. But it is the one that we use the most when we are submitting commands to our database. Any questions on that? That makes sense? And now you guys know that the keyword, the actual code words that you would need to make this work are going to be something like inner join. And actually, maybe it's going to be natural joins. It would be in an SQL database, not in Access database. Access uses a subset of SQL commands, but doesn't do everything from SQL, plus it tries to do put its own spin on its SQL language. It allows you to put in VBA commands that do stuff, and that means any SQL that you write in Access that has a VBA command in it will not work on a true SQL system. Only work in another Access system. And so you're self-limiting yourself if you're using the special stuff that Access allows you to put into a language that weren't originally designed for that language. But every company does that, really. They like locking you into their products. Once you use Microsoft Excel, they never want you to go off and use Google Sheets or something. They want you to like their special tricks so much that they capture you as a customer. All right, so I've got 5 minutes. I can probably introduce a great big huge new topic. Now the next topic I want, okay, so this is just a table that I copied from your book, which is basically what I tried to write on the board there, because I forgot this was coming up. But this is basically showing all of the fundamental data types, plus natural joins, since we kind of like that one. And I guess it's not showing subtraction of the fundamental data types. We threw out subtraction because it's so rarely used, and we actually put a useful one in there. And they do actually give a real-world application of bow tie there. And so again, bow tying instructor and department together is just going to build one combination table out of instructor and department. But it's only going to show those rows that have the same value in their common fields, and I bet if you had your schemas out right now, you would see that the only common field between the instructor table and the department table would be the department name or something. I think they both have that column name in them, and so this would basically show you a list of all of the instructors on campus and the details of the department that they're assigned to. And we're assuming that no instructor will be assigned to 2 separate departments, although that would also work. If somebody were in the computer science department and the tag department, they would just, their name would, in the instructor table, would match to 2 records in the department table. And so that's like having multiple actors combined with the same movie in my application. Otherwise, hey, they did the same union thing with instructor and student names that I did, and they did not give any reason why instructor cross department would be useful at all. It just outputs all pairs of rows from the 2 source relation, regardless of whether they have any shared values at all. It's just an intermediary step. All right. Did I waste enough time? No, I've got 3 more minutes to introduce a great, big, huge new topic. Sometimes we're going to see this arrow, we might see this arrow symbol in these relational algebra statements, and that's basically like take the result of these operations and put it in this table. We're going to give this table a new name. It's basically like combining multiple variable values into a new variable in a programming language. So that's what arrows is going to mean. And so if we just take the student table and then assign it to the A variable, we're actually creating a new table named A that has all of the same rows in it as the student table did. Hey, you guys have been collecting flights still, right? I mean, ever since you handed in your assignment with graphs for the first couple of weeks of flight changes, you've been collecting data every day on these flights. Now you're getting close to being able to give me like a month's worth of data on the 3 flights that you're tracking. DFW, Boston, and New York City, right? Because This is the graph that I got off of Google Flights, since that's the one that I'm using. And actually, this is from, I don't know, 4 years ago or something. And so those dates are not this year's dates, I do not believe. But they do go from Tuesday to Sunday. That's what stays the same from year to year of this class. It's just the actual numbers for the dates change. And yeah, I don't think many of you are tracking $150 flights to any of these destinations. This may have been like in 2020 when nobody was buying plane tickets for a while. Because, I mean, you guys are going to tell me if it's a good time to buy these tickets, right? You're going to be able to tell me, well, the price has gone up, or even better, the price has gone down since I've started tracking, right? That's why we're doing this, so that you can suggest to your customers, to your boss's customers who's having you do this, if now is a good time to buy a ticket from your airline company. And by the way, according to your boss, now is always a good time for people to buy tickets from their airline company. All right, you know what? I am not even going to go into the next subject. I've wasted enough time. I think I'm happy enough with you guys' progress. I'm going to cancel Friday's class for you. So you don't need to bother showing up to class on Friday. However, I am probably going to give you an assignment that's going to pop up in D2L on Friday, but it's going to be due a week from Friday, and it's going to be homework 2B. Make me 3 graphs of all of the data you've collected so far, even if it's not a month's worth. Show me that month's worth. And by the way, one of those graphs, the Boston flight, is one that we stopped tracking for like the last 2 weeks of September, or was it the first 2 weeks of September? I forget the details on that. There was one flight where you stopped collecting data, right? Because we want to test and see if we're looking at a flight fare for every day for 2 weeks or something, and then we stop looking at it, will the price go down, right? Because that's what I'm afraid those airline companies are doing is if I'm looking at the airfare every day, they're looking at me and thinking, oh, this guy really wants to buy this flight. And so they are not showing me the cheapest rates, right? And so I want to simulate, okay, well, I've lost interest in this flight, and so that guy's not checking it anymore, and so the next time I check it, maybe from a random internet address at the library, I actually see the price has miraculously gone down over those last 2 weeks when I wasn't checking the flight. That's the idea over that. You guys stopped checking, right? Because if you have been checking that third flight every day, then that trick's not going to work, right? You can pretend like you don't have data for those weeks, but the experiment won't work. I don't know whether you have been not collecting fares for a third flight for 2 weeks or not, from the blank expressions I'm seeing in the classroom. All right. I mean, even if you forgot to not take its data for 2 weeks, show me all the data that you have in the upcoming assignment. And if you want to, if you forgot to do it during September, try it during the first 2 weeks of October. And we'll go with that, because really it's going to be something that is only going to work on a person-by-person basis. It's not something that we can put together and the group data is going to show us something like that, although it might. Whatever. Anyway, thank you for your attention. I will see you guys on Monday.